Well, it's Class D time at last. Now, first of all, before we go on to have a look at the project and talk about it a bit, there's some things I have to confess to. My knowledge of Class D is not very good. Now, you probably think I'm not the best person to talk about a project, but I'm looking at it from the point of view that, like many of you people that watch, where you don't know much about it either. You know the basic principles, you know how it works, and I don't want to go into how it works because there's plenty of really good videos out there explaining. But the first thing is that we're looking at getting the best quality possible without spending hundreds and hundreds of dollars. And I think I've probably struck a good compromise here. I'll go into later why I've chosen this particular model and its claim to fame, and we'll talk about whether it's good quality, mediocre quality. And I have to say that from my past experience, I prefer generally Class AB for many reasons. But saying this is a very nice sounding amplifier, and well, I won't go into it right now, but I'm learning as we go along. I've been working with valve amplifiers and Class AB for the past, I hate to say it, but 50 years. And that's where my general expertise and experience lies. But Class D has got a lot going for it, least of all the high efficiency, and compared with, say, a valve amplifier, which draws megawatts in comparison to this, and doesn't produce any output power. Anyway, let's get into the video, and we'll have a look first of all at the ingredients that we're going to use to make this, most of which I've spoken about, and you can go back into past videos if you want to see more about specific items. Anyway, let's get on with it. Now, this isn't actually the circuit diagram of the amplifier in question. It comes off one of the application notes, but it shows you primarily the chip, the IRS 2092, which is really the heart of the amplifier. It is the complete driver circuit, and unlike most Class D amplifiers where the one chip is everything, the power transistors or FETs and everything, and it's very small, and inherently it gets very hot, and inherently it isn't supplied with a heatsink, or if it is supplied with a heatsink, it's woefully inadequate other than just general music into an 8 ohm load. But the reason I've chosen this particular amplifier is because I was quite impressed with the 2092, and as you can see from this particular circuit diagram, it does show the output as a pair of leading into a pair of FETs, which this particular amplifier does do. It's not this particular FET, we'll talk about that later. As I say, this is an application note and doesn't represent this particular amplifier, particularly around the input stage where it doesn't show any of the input transistors, but talk about that presently. Now, the FETs that it does use on the output is this one, and it's the 4019. And its claim to fame, as you can see by the picture there, it's just one package and it contains both of the FETs. Now, this is quite an amazing FET. As you can see from the description there, it can deliver up to 200 watts into an 8 ohm load into a half bridge configuration, which is what this is in fact. Now, we're not trying to get anything like 200 watts, but it will deliver that sort of power depending on the supply voltage into a 4 ohm load. I'm aiming for just over 100 watts with this, but we shall see. Now, because like most of these Class D products, the actual power output is somewhat I wouldn't say optimistic, but they rate the power outputs somewhat differently to me. Now, to me, I always rate maximum power into a specific load at a specific band of frequencies, and most importantly, at a specific distortion level. I don't normally quote the specific distortion level, but when I look at the sine wave, the moment it starts to clip, I will then reduce the power slightly, and whatever that power is, I measure that. Now, to me, that's how you should rate an amplifier, because who cares if it will deliver 6,000 watts at 10% distortion? 10% distortion sounds awful, particularly when it's clipping, because you're turning your sine wave effectively into nearly a square wave, because the top certainly does square, and you can't listen to music in that position, so why rate it like that? I'm just knocking my torch over now, sorry about that. I might edit that out. Now, these are some of the published specs of this particular amplifier. In this particular version I'm working on, we're using about 50 to 52 volts, and the only way you'll get 500 watts is if you were to bridge it into a very low impedance. Well, we're not really after huge powers. I mean, bear in mind 100 plus genuine watts is a powerful amplifier, but I'm looking for the quality side of it, not the quantity. There's plenty of people having amplifiers that are giving millions of watts per channel, and they tend to come from the Middle East and Far East, I have to say, where their versions of power differ slightly from mine, i.e. 3 or 4 times. Anyway, as you can see, the quoted, or one of the quoted figures is distortion levels at 0.007%. That's into 60 watts into 4 ohms. Now, I don't propose to use this amplifier into 4 ohms at all, because along with most amplifiers, you generally get better results into 8 ohms. I'm not disputing you get more power, you could run it into 2 ohms, but when you start getting into levels like that, what are the speakers you're talking about? PA speakers? Well, hopefully you're not building this with PA speakers in mind. You might be unlucky enough to have a 4 ohm pair of speakers, but when you start getting down to those sort of levels, losses in the cables and switches and contacts really mount up, and the distortion of the amplifier goes up generally quite appreciably. So 8 ohms, if you're going to go out and buy loudspeakers, buy 8 ohm speakers. Another point to mention about that is an 8 ohm speaker is generally only 8 ohms at a certain frequency. An 8 ohm speaker you can possibly expect to drop down as low as 4 ohms at certain frequencies, depending on how good the crossover is. I mean, it shouldn't, but invariably you'll find it does, and the impedance tends to rise as you go up in frequency. Anyway, we won't dwell on that. But looking at this, you can see it's capable of quite amazing currents, and that's mainly because you have external FETs on it, and the FETs are mounted on a separate heat sink. Now, you remember previously I showed you the application circuitry. Well, this is the FET here, the dual FET, and here is another transistor. Now, I'm not quite sure what that does because there's no reference to it, but it is in fact an H669A, which is an NPN medium power high frequency transistor. But here we have another power transistor, and this is quite an old one, and it's a tip 42C. Generally an output transistor used for lowish power, and here is the complement, the tip 41C. Now I don't know what that does, because I should point out that both of these actually get quite hot, and I'm thinking of actually investing in a heatsink or an extension piece of metal here. I'm sure it's quite within its capabilities, and one of the odd things about this amplifier is the heatsink gets medium warm even under quiescent conditions. And the ironic thing is, or the odd thing about it is, when you're thrashing it to 100 watts or so, it doesn't get any hotter. I haven't quite worked that one out yet, but it doesn't. I mean, it simply doesn't, because all the power is generated on this FET, or by this FET, I should say. Now here's a front view where you can clearly see the tip 41s and the 669A, and there is the FET. You can see it does in fact have 5 legs to it. Other than that, there's very little here at all, other than just the general inputs. Now this is the output end of the amplifier, and you can clearly see the filter choke and the supporting capacitors here for the output filtering. Now this choke gets quite hot. Now it's always difficult to say how hot quite hot is, but you can put your finger on it and it's almost too hot to touch. You can leave your finger on it, but it's noticeably hot. And when you think that's just basically a coil of wire in a ferrite core, but the whole power of the amplifier goes through it, and it still gets hot even under quiescent conditions, again because it's filtering out the carrier. This is a photograph of the underside of the board, and just to go through some of these two diodes here are across the output FETs, and if you watch my previous video on this when I was testing it out, I was stupid enough to connect the positive and negatives around the wrong way, and it's these two diodes conducting which blew the fuses rather than blowing up the rest of the circuitry. So very wonderful diodes. But there is the driver chip, which is the claim to fame of the amplifier, so to speak. And there are just other supported components around there. There doesn't seem to be any other amplification, so I guess it's relatively sensitive. You can drive this without a preamp. I've been testing it with my computer, and I can reach full power without any form of preamp. But if you're going to run it from a telephone, for want of a better word, you will probably need a preamp in front of it. This is the rectifier board that I'm going to use. Now I have made a separate video about this, so I don't really want to go into it all again. Just put myself there. No, I think we'll go there. But its claim to fame is it does have a lot of capacitance, namely 176,000 microfarad, and there's 4 per rail, so that's the positive rail and that's the negative rail, or vice versa, it matters not. But its main claim to fame is, here we have the 4 rectifier diodes, and they are Schottky diodes, and again their claim to fame is very fast, very low internal resistance, which means you're going to get low voltage drop across the output due to the internal resistance of these diodes. And also because they're fast, they don't tend to ring, or oscillate's not the word. I think ringing's probably the word, because again they have these capacitors across them anyway, which I think it's those two. Can't remember. I think it must be those ones because they're across the main filter capacitors. But the output from it is very nice. These diodes run cold under high power music, but if you're going to sine wave test it into 4 ohms, they do get quite hot, because into 4 ohms, if you think the amplifier is developing 200 watts per channel, that's a lot of amps going through there. And I would suggest, if you're going to, why you want to develop 200 watts into 4 ohms, both channels driven, I cannot imagine, because you'll need one hell of a heatsink to dissipate that kind of power. But if you are that way inclined, you will have to mount those on a heatsink, or just do the tests very quickly because they get too hot to touch. Now, as per usual, you've got to put this lot in a case, and I know you've seen this. If you've watched most of my videos, you've seen this cabinet many times, because quite frankly I did pay actually a bit less than that, but ironic thing is we don't need heat sinks on this because the modules already have the heat sinks. But to get a cabinet of similar size that doesn't have heat sinks actually costs more. So I know it's a ridiculous situation, but I'm considering taking off this heat sink and putting a nice wooden panel on there each side, because these heat sinks are totally superfluous to this project. But you can't buy a smaller the same cabinet without the heat sinks, so I'm either going to leave the heat sinks on and just leave them on for display, or take them off and put a nice piece of walnut or something on the side there. Time will tell. Now, this is where we are so far. I put the heatsink on there to give you a scale of what we have. The back obviously goes along here, the other heatsink here, and the front panel will go here, which I haven't dealt with yet. Now, as you can see, there's nothing mounted on the heatsink at all. But here we will have the speaker protection module. Now, don't laugh that I'm connecting it to a heatsink. I know it won't get hot, but it's the only place I've got left to put it. Now, the transformer I'm using on here can only be described as overkill. Now, this is a 500 watt potential transformer. It's 36-036, which will very nicely give us about 52 volts DC plus and minus. I could have got away with probably a 300 watt transformer, but I've got this in stock, so I was going to use it. And it also has on here some other low voltage windings, because the protection module and the input relay module requires an AC input of about 12 volts. And I've got many voltages available here. So this transformer means I don't have to have another separate transformer to get the AC we need. It will also power the on LED. Now, you may say, why am I going to power it from AC when obviously you'd normally feed a LED with DC? Well, I've done this in the last 2 amplifiers, because then with a 12 volt AC supply, all you need is one resistor. If you put a diode in there, I find it tends to flicker, so you then need to put a capacitor to smooth it. But I find that it's no problem running it off AC. The camera can't see it flickering, and certainly by eye you can't see it flickering. I know it should be, but 50 cycle, effectively the LED is its own rectifier because it's a diode. Here are the two modules already mounted, and I've started to mount the connect the cables with the fuses, and that's really all I've done so far, simply because I'm missing some key ingredients. But I'm going to test it in this form shortly. Bearing in mind, I know that all this stuff works because I've had the thing on the bench, testing it off and on now for about 3 weeks, mainly to decide if I liked it. It actually produces a very nice sound, very clean and so powerful. It just gets so loud. Here's the rectifier board, and along the front here we have the input from the transformer with the center tap going to the center. Nice and easy. I've almost sort of color coded as well. Right, this video is beginning to get a little bit long, so I think we'll continue it later when I've got some more components in. But this is going to be a heavy amplifier, mainly because of this. But there is a reason, and I would always suggest, if your funds allow it and the space in the cabinet allows it, always overrate the transformer, because the thicker the windings, the lower the voltage drop is going to be, and obviously the transformer will remain virtually cold, as this one does. But the main thing is, the higher the amperage windings, the lower the voltage drop is going to be, and the lower the power supply is going to sag. And along with these shocky diodes and this quite hefty rectifier block, you can cane these amplifiers, and the voltage drop is about 1 volt. So if you just use a conventional rectifier and a lower power transformer, you could find the power supply sags by 4 or 5 volts. And as volts equals power, it will limit your maximum power, particularly its dynamic range. So as per usual, thanks for watching, and keep a lookout for the not too distant future, depending on China Post, for the next part, and get it all going. Look forward to that. Don't forget, any comments, I'm very pleased to answer any questions. Positive and negative comments, you're welcome to, and I will print them, I won't delete them. I hope there's a few more positive than negative, but we shall see.